8.5, we're solving exponential equations. Our goal is to solve equations in one variable using a variety of strategies. The strategies are those laws that we learned last section. We're talking about radioactive substances. There's 200 grams of radioactive radon, and 16 days later that gets reduced to 12.5 grams of the radon remains. So we're trying to determine the half-life of the radon. So there's a formula here that we've learned last year for half-life. So that's our new amount of material is our initial amount of material times the rate at which it's decreasing to the exponent of the time at which the half-life decreases. So that's T over H. So we substitute our values in and we find that the unknown variable is actually part of the exponent here. So previously, what we had to do in grade 11, and we've done questions like this before in grade 11, we need to find a common base and then we can equate the exponents. Okay, so the first step is to isolate the variable. So we get to here and we have 1 over 16 is equal to 1 over 2 to the exponent of 16 over h. So we need to create the 1 over 16 the same base as a half. So we know 1 over 16 is actually the same as 1 over 2 to the exponent of 4. And that's because 1 to the exponent of 4 is still 1. The denominator 2 to the exponent of 4 is 16. Any questions on why that is that?
So, you said 1 to the exponent of 4 is 1?
Yeah, so if you take 1 to the exponent of 4, you're still going to get 1. And if you take 2 to the exponent of 4, you get 16. That's why 1 over 16 is the same as 1/2 to the exponent of 4. Okay? So if we have them both now with the same base, we can equate the 4 and the 16 over h. So we have 4 is equal to 16 over h. And then we rearrange this. We get h is 16 divided by 4. H is 4. Okay? So the half-life then is 4. And the original question said in days. So it would be 4 days. Okay? Any questions about that? So that's what we've learned in the past. We've done that. We've done guess and test. We haven't solved this using logarithms, and that's what we're going to do today. So there's our answer for the half-life of radon is 4 days. So the preferred method, of course, and the one that we're learning now, is to solve equations algebraically by taking the logarithm of both sides. So working with the same equation, we do the same process to reduce this term. But now, rather than trying to find the same base of a half, we can go directly to decimal values here. So we do 12.5 divided by 200, we get 0.0625. That's fine because now we can take the logarithm of both sides. Using the power law of logarithms, we know that the log of a number to an exponent, we can drop the exponent down. So that's what happens here. This 16 over h comes down. Okay. Now we just isolate as we normally would for the h variable. So h is coming up over here. The log 0.0625 comes down here. And we get h is 4. Any questions? Okay, straightforward. The third solution uses graphing. Again, very similar. We just end up graphing the equations and find the intersection point between the two. Okay, and we find out that that intersects down here at t is equal to 4. Okay. Again, preferring though the logarithm algebraic solution. Example 2. Selecting a strategy to solve an exponential equation with more than one power. So this is a tricky one, I would say. This is probably the only difficult part of today's lesson is understanding what to do here. Okay, here we have a base of 2, an exponent x plus 2, minus a base of 2, an exponent x. So I think some of you might be tempted to just start taking the logarithms because that's what we've been focusing on. And it might be kind of, well, it is a little misleading to think that we could do this, right? We could just do log . Okay, that might be the first step that we'd want to do, and then we can drop our exponents down. However, there's a problem here, okay? This does not work, okay? So if you have something like 6 minus 4 is equal to 2, okay? You cannot do log 6 minus log 4 is equal to log 2. Okay? This does not work. Okay? You can't take logarithms of terms that are separated by addition and subtraction terms and just take the logarithm of the other side and have this work. So if you were to try this on your calculator, you wouldn't get the right answer. Okay? The only time you can take a logarithm of both sides is when it's like, say x is equal to 7. If it's only one term on either side of the equation, okay? Or various terms multiplied. So this log x is equal to log 7. So this works, okay? When you have terms separated by subtraction signs, it doesn't work, okay? If you had something that looked like this, something like this, because these are all multiplied here, you could say log all of this is equal to log this. Okay, this would work. Okay, but this doesn't work. Okay, this doesn't work. You guys see the difference? Hope I'm not confusing anybody, because I'm trying to get some clarity of when you can log both sides. You can only log both sides if you have one term on either side. And what I mean by one term are different variables separated by either multiplication or division. As soon as you separate variables or terms by a subtraction or an addition side, they constitute different terms. Does that make sense? You know when we say gather like terms? Well, 7x is one term, but 7 plus x is two terms, right? So as soon as you start adding or subtracting, that's when you get a difference of terms, okay? So you can only log one side and equate it to the log of another side if you have one term, okay? Any questions about that? So that's why we can't, the reason I brought all that up is we can't just take the log of all of the variables here. Like we could multiply everything by 2 and they would still be equal, right? We could say 2 times this, 2 times this, and 2 times that. That would work, okay? But we can't just take the log of each side. It's similar to exponents, right? You can take the square of one side and it can be equal to the square of another side as long as there's one term. As soon as you have two terms, you can't just square them, right? So I'll give you one more example. If we had 2x plus 3 equals y, okay? You can't say 2x squared plus 3 squared is equal to y squared. Okay, you cannot do this. It's not equal. Okay, and I think most of you understand that, right? Whereas if we had 3x is equal to y, you could say 3x squared is equal to y squared. Does that make sense? You see how the rules of logarithms are similar to the rules of exponents? Okay, that's very important, okay, because the minute you just start logging everything and dropping things down, you're going to get confused quick when your answers are not correct. Okay, so having explained all that now, we know we cannot just log these to drop the exponents. You have to realize, and this is a tricky part, that these two terms can be factored. Okay, there's a common factor here. So one way we could see that is if we rewrote 2 to the exponent of x plus 2. We could rewrite this as 2 to the exponent of x times 2 to the 2 squared. Right? When we multiply two terms with the same base, we add their exponents. So having rewritten it like that, then I think you would see that the 2 to the exponent of x term is common, right? So this minus 2 to the exponent of x. You can see here now that these two terms are common, so I can actually factor that out. So I'm dividing both sides by 2 to the exponent of x. I'm left with 4, so 2 squared minus 1. That's to here. Any questions there? Okay. Once I have that, I have 2x times 3 is equal to 24. I can divide the 24 by 3 and I get 8. And then this is relatively easy. You can even do this in your head. We know 2 to what exponent is 8? Well, it's 3. You can make 8 to the base of 2, and you can solve for 3. Or at this point, we could then take logs. We could log here now, because we only have 2 terms on either side of the equal sign. Okay? But we really don't need it. It's pretty simple from that point on. Okay, but it was tricky to identify the common factor there. All right, example 3. So we have an investment problem here. We all know the equation for compound interest looks like this. We plug in our initial amount, which is 2,500 for P. That's our principal. It says it grows at a rate of 4.8. So that's our interest rate here. Remember, we divide that, of course, by 100, so it becomes 0.048. So that gets added to 1. Okay, and then it's asking when will it be worth 4,000? Well, that's the future value, and that goes in for A as the amount. Okay, this is a review from grade 11. Okay, so we plug all those values in and we find out that the unknown is actually in the exponent. Okay, and previously we had to guess and test, or we had to find a common base. Now with logarithms, this becomes quite simple. Once we get it to this point here, we just take the logarithm of both sides. N is allowed to drop down in front, and we solve for n. Any questions here? Last example. It asks, so we have 2 terms now to 3 decimal places. Because there's only 1 term on either side of the equal sign, we can take the logarithms and drop those exponents down. Remember, we're going to take the logarithms of both sides, so that exponent drops down, and then it's just a simple process of rearranging and solving for x. So here we have x plus 1 log 2 equals x minus 1 log 3. We multiply using our distributive property. We get this value. Now we rearrange, we put all the unknowns to the right hand side. We divide by those logs and solve for x. Pretty straightforward. In summary, two exponential expressions with the same base are equal when their exponents are equal. For example, am is equal to an when m is equal to n, where a and m are all real numbers and a is not equal to 1. If 2 expressions are equal, taking the log of both expressions maintains their equality. For example, m equals n. Okay, remember, now that's only for when there's 1 term on either side of the equality, right? Then log am is equal to log an, where m, n are greater than 0, a is greater than 0, and a is not equal to 1. Remember, when we use our logarithm laws, we have to have those m and n values to be greater than 0. Finally, you need to know to solve an exponential equation algebraically, take the logarithm of both sides of the equation using a base of 10, and then use the power rule for logarithms to simplify the equation and solve the unknown. Power rule means you're dropping the exponent down. Sometimes an exponential equation can be solved algebraically by writing both sides of the equation with the same base. If possible, setting the exponents equal to each other and solving for the unknown. Why do you guys think that finding the same base might always not be the best way to do it? Or what's a disadvantage of doing that? Can anyone tell me? You know, where we find the same base and we just equate the exponents? Why does that not always work? Sorry? I can't hear you. I think what you mean is it could be a non-terminating decimal. Is that what you mean? So in other words, like, it's not always an exact base. It's not a whole number. Okay, so he's saying fraction, but yeah, it could be the base of whatever number we need to get to. It might not be a whole number. So in that case, you can't just get the bases the same, right? You'd have to guess and test and do all these different things. So it might not always be that simple as finding the same base, whereas logarithms will always work. Exponential equations can also be solved with graphing technology using the same strategies that are used for other kinds of equations. Any questions?